You okay? I assume everybody is back. I got a stretch and some more coffee. Everybody needs more coffee. We're running a bit behind. It's 4:30 and we're scheduled to go to 5:30 or so. So I think this is going to have to be a bit quicker than it was supposed to have been. We're going to end up covering a lot of ground, I think. A lot of the stuff that we cover is not going to transfer terribly well to NanoHub. NanoHub does not like file IO because of protection problems, probably. But in any case, we'll see how far we can get. Remember, this is being recorded and may show up on the internet somewhere someday. So let's see, where should we start? Hopefully you can see my screen here of my slides. Here's a brief outline. We start off with writing data to files, and if you can write the data to files, it's pretty easy to read it back. We'll talk a little bit about running parameter scans and running replicates, a little bit about sensitivity analysis, and then try to finish with parameter files and some best practices ideas. There's a zip of zip in the today's folder online. I will put this link into the chat if you want to download this zip. So that's a zip of zip. So it's got this PowerPoint in it. It also has these 5 files. These are zip files of CompuCell projects. If you want to follow along or check back and kind of catch up, this middle set here is meant to be sequential, so that if you get behind, you can just load up the next one in the series and get caught up. Okay, so we're going to start with writing data to files. You might have seen a little bit of this earlier this week. Twedit does have some tools to help you do it. You can also use standard Python code. There should be a C there. It's like any other Python program. You can open and close files, control where they're at. Usually you'll want to open a file in your start function, write some stuff into the file in your step function, and then close the file in a finish. And the demo and the working set is writing two files, excuse me. So as I said, there's some helpers in Twedit, and I will show you some of them. For instance, so here's my little demo of just writing the files. It's pretty much straightforward. It's just a cell sort. So normally you would open a file in your start function, do some calculations, and then write some stuff in your step. In this case, we're only going to write it once, just at step 50. And then just to be a nice citizen, close all your files with the finish. Also make sure you don't lose any data. So as using the Twedit shortcuts in CC3D Python, there's Python utilities, and you see these are almost all related to dealing with files. Get the steppable class name and so forth. In general, or one common thing to do is open a file in the output directory, which on NanoHub is a little weird, exactly where the output directory is, but on most desktop systems, Linux, Mac, and Windows, that would be in your standard CC3D workspace or whatever folder you specify in your player settings. We'll talk about some of these other ones in a minute, but if you go ahead and click on Open File in Simulation Output Directory, you get this little insert, which is pretty straightforward. The only 2 things you really need to change is you have to give it a file name. It should be quoted. And you have to decide if the file should be read, write, or append. So W for write, A for append, and R for read. This returns 2 variables. The actual file object, which is what you generally refer to, and also, just to be nice, it returns the file path. But in the future, you'll refer to this particular file as this file object. If you're going to be using this file object in any other class, for instance, open and start, but you want to use it in step, you'll probably need to include the self tag onto it so that it can be used in other places. So I'm going to take out my insert that it did. Just delete it. There we go. And here is my edited version of that little helper script. So my file name, I define up here, logfile.txt, and this is a file being opened for write, and it's self object. So this is writing to your standard output directory. If you want to write to your project directory, it would be the directory where this actual CompuCell code is located. It's a little trickier, not too much trickier, but you need to import the OS and then open up the file using that. Import OS is actually in the Python CC3D Python utilities, import OS. And so that once you do that, you can get the directory of this actual file. So here's the script to do it. So this is where this actual Python steppable file lives, is now in FileDir. FileDir up one just goes up one. You can look at the code later if you ever need these little widgets. So this goes up one directory. So now instead of being in the simulation folder, this is in the project's main folder. And that gives you a path, and then you can append a file name to it and use standard Python open to open that file name for append. So this is a handy way to do it if every time you run your job, you want it to append to the same log file. So just so we have a complete thing, we're going to define our cell target volumes. We're going to start running the simulation. At step 50, we're just going to count how many of our two cells we have, A cells and B cells, or condensing and non-condensing cells, usually in cell sort, but here I named them different. And we're going to build a text string to write to the output files. Writing to a file, so you need to write strings and not numbers in general. So we have to convert our numeric values with string. We can get the count of cells just using the same list we use if we're going to visit all cells of a given type. So the len of self cell list by type, self A cell and B cell gives us our cell counts for the two cell types. So we create a string, and then our self object file write output text, which is that string, and then there's another one because I opened two files. Remember, one's in the normal output directory, and one's actually in our working directory. And we're just doing that at step 50. And then at finish, we're going to write a little closing message in each one of those two files and then close them both. So if we run this, where'd my player go? It's going to be a little slow to start up here. The slide deck has basically everything I've said on slide. So import the widget, edit your file name. Don't forget to close the file. How to write to the project directory. Again, how to insert the import OS and edit it so that it's writing to a file where you know where it's at. So here's the sort, and it's already done because it is such a tiny little project. And now if I go to, if I remember where is that. So this is my CC3D workspace. And that's by default, CompuCell writes my job name and then a timestamp. And here's my log file. Get it to open. So there's everything I had written to the log file. How many cells I had at that particular step. I think it's always a good idea to write a starting message in a file and write a closing message to the file. That way, if you go back later and look at the file, you can tell the file was closed normally because it's got your closing tag in it. So I know I got to the finish statement that officially closed the file, which means I got to the end of the run. So that is the one that's in the standard output directory. Yeah, see if I can find my other output. Now I've lost track of what file I'm in. But in the top left, wherever this file was loaded from, actually in Twit. Okay, it's in my CompuSol file. There it goes. So this is the other log file that was written to the top of the file. And you notice in this case, I didn't write a header and closer, which is not a good idea. You should definitely write a header and closer to those files. So this is actually probably the wrong file. But in any case, in the top level directory, there it is. So this is the new one. So this is my regular working directory for the simulation. And here's where it has written my log file. And that one looks correct. So I got my starting message, the how many cells were at that particular step, and then my closed. So that's two ways of writing either to the standard output directory or writing back up into your main working directory. So this is my regular old working directory. It was set up so that this one will get appended to if I run my simulation again. It's a very short simulation, so it won't take very long. Now it's done. It says this editor is telling me my file has changed. So there's the result from this new run. The other write would be written into the our standard output for CompuSol directory, which I won't show. So that since I did a new run, I got a new output directory, and it'll have just a single entry file in it as well. So that's the easiest way to read and write. If you're actually going to read a file, it just changes the mode. And you can do a quick Google search on Python reading from a file to figure out what the command is. So that's reading and writing to files. Appending to files, writing them in different places. Reading and writing files is one of the things that tends to not transfer very well from platform to platform. Especially if you have hard-coded paths. Obviously, if it's got my username and my path somewhere, that's going to be a problem to transfer it. The way I've done it here, though, I have nothing hard-coded in the Python about the path. It's retrieving the path from CompuSol. So the file should move from machine to machine without any problem. Okay. So reading and writing the files. Next, we're going to go to parameter scans. So a parameter scan is an attempt to exhaustively walk over one or more parameters in your file, and it automatically run the simulation as you change those parameters. So with the parameter scan, you explore a range of values in an automated fashion. You want to know what your cell lambda volume should be, and you'd like to try 3 or 4 values, but you don't want to sit there and have to change your script in Twedit and then run it and then change the script again and run it. So parameter scans will let you set it up and say, I want to do 5 runs with these particular sets of values. You have to be careful about parameter scans, though, because it is a combinatorial problem. If you do 3 values for 1 parameter, that's 3 runs. If you do 3 parameters for each of 2 values, that's 6 runs. If you do 3 values for 3 parameters, is 20. Excuse me, 3 of 3 was 9, and the next one up, 3 parameters, 3 values is 27 runs. So real quickly, you can get into a combinatorial explosion where you just way too many things to scan. So I had this example here. If you wanted to scan 10 parameters with 5 values each, It's a 10-digit base 5 number. That's 5 to the 10th. That's a lot of simulations. You're not going to be able to do it. So there's a limit on how many you can do, what's practical. And that depends on how many parameter scans you want and how long it takes to do one simulation. The simulation we're going to be using runs really fast. So we could actually do quite a few. In general, your simulations won't run in the 10 or 20 seconds at this demo that we're going to be using. So we'll move on. One thing about parameter scans is once you put a parameter scan into a project, it's kind of difficult to get it out again. So it's always a good idea to get your project working the way you want it to, and then make a copy of it and use that one to do your parameter scan. Like I said, it's not easy to get rid of. One thing you definitely want to make sure of is before you add the parameter scan, if you're going to save any screenshots, you want to make sure that in your preliminary version project, you've got screenshots saved on, you've got your windows open, you've clicked on the camera for any other screenshots you want. Because once you move into the parameter scan, you're not going to have access to those functions because it's going to snap through all the stuff automatically. And you won't have time to click on the camera icon and stuff like that. So we have another model. If you're playing along at home and you want to open up cell sorting base, we'll go get it. Take me a moment to get there. So this is the thing we're going to, this is, again, another cell sorting. This one's written a little different. I'm actually using condensing and non-condensing cells. It's very straightforward. It's very similar to what you've seen several times. If we run it, take a moment to start up. So our window of our cell sorting, we've also got a metric being calculated, the hetero contact area is being plotted here, and we'll talk about that in a minute. So we'll go back over, stop that. So like I said, regular old condensing, non-condensing, very straightforward. Now, if you're going to do a parameter scan, it's a lot like model fitting, is that you need some output that you can judge how good the simulation was. In this particular case, what we're trying to do is get the cell sorting to work best. So we need some metric that describes how well cell sorting works. And that's not necessarily, this case, it's not too complicated to come up with a definition of what is a good simulation. In other cases, it's actually kind of tricky to figure out what a single numeric value is that you can assign to the output of your simulation. If you're fitting data, usually that metric would be your residual error. But a lot of times you don't have data to fit, and so you need to come up with some metric. In this case, we're just going to come up with this very simple metric of just counting how much surface area there is between the condensing cells and all other cell types. And that's going to be our metric. And in the run here, that's what's being plotted. And in this sample, it's pretty straightforward. It's this part. We are going to visit all cells of self-condensing, all the condensing cells. So we're going to visit all of the neighbors of that cell. And then if the neighbor is not of the self-condensing, it's a different cell type, we're just going to sum the heterosurface area. There's also a possibility that the neighbor is actually not a cell, but a media instead, and that's what the second catch will catch. So this will sum up non-condensing and media surface. And then we plot it to our plot. At the end of the run, we'll also write this. We're just going to output it to the screen. So that's going to be our metric. Pretty straightforward, but if you're going to do a parameter scan, you definitely need a metric. It's possible you could also write screenshots and just go through all of your outputs and look at all your screenshots and make some judgment call. I think it's usually better to have a numerical value. Okay, so now we have some metric. Now we can actually start thinking about how you run a parameter scan, or what you would parameter scan, what you're trying to optimize in a cell sorting experiment. So this is basically the core of what really makes the cell sort work is your J values. That's what's driving the sort. So presumably one of the best things to adjust to get the best cell sort would be the J values. And just kind of by gestalt and practice, I've got a pretty good set of J values there. The cells sort pretty well. You can see a demonstration down here, starting with a random set of random field of cells. It's doing a pretty good job of sorting. It's not perfect, though it's probably because the simulation is not going long enough. But this is probably where you want to do your parameter scanning. So to start a parameter scan, we will go ahead and use this file here that I have open, this demo, but I'm going to fork the project. I'm going to make a copy of it so that my original file stays put. And did I miss it? There we go. Then give your quick name, just so I'm not working on my original file. I'll just get back to it if I need it. So as I said, this is probably where you want to be fiddling if you're trying to get a better cell sort. It's in the J values. And so now we're going to add a parameter scan to it. And there is tools, a bunch of tools. I got ahead of myself, as I say here, to remind myself. But first, before we can add the parameter scan, we need to add that metric into it. So there's another file that actually does that. And basically what we're going to do is, too far back, add a new steppable, which is the Python CC3D Python option to add a new steppable. And in that steppable, we're going to calculate that metric of contact surface area, heterologous contact surface area. So the new file will have that in it. For the time being, I'm going to kind of skip over that. So that's the cell sorting base, actually the one I started with anyway. But now, so now that we actually have the metric, we can go back and say, okay, now we can really add the parameter scan. So fork the scan. I just make a copy of your folder so that you're not editing your original, because like I said, it's hard to take a scan back out. It can be done, but it's a lot of work. And now we're finally ready to actually add our scan. So here's our project we're going to add a scan to. These are our values we probably want to be manipulating. So you come over here to the file project list and do a right click and say add parameter scan. And now we get a new entry here, parameter scan, or I can open it up and it's a JSON file. And to start with, it's basically just has a header in it. It doesn't actually say anything of interest. But that's where our scan information is going to go. We go back over here. And now we need to decide what we're going to scan. I think medium to condensing J value. Let's explore that one a little bit. What you do is you highlight the numerical value and then right click and pick add to scan.
There was a question in the chat about how do you open the parameter JSON file.
Okay, so once you've done add parameter scan, it adds this new entry into your file list. And by default, that one doesn't automatically open. So you'll need to click next to it, which it'll show you the file. Double click the file and that'll open it up here. So see, now I have 4 files, my base XML, my registration file, my Python steppable, and my JSON spec. Okay, so now we're going to add this value to it. Select the whole value, right click, add to scan, and we get a dialog. First thing it wants is a name, something that we can call this thing that we're changing. it's nice to be a name that's relevant. This is the J value from medium to condensing. So we can just call it JMC. So J value, medium to condensing. Once a start value, our value was 10. We don't want to do too many values here. So let's do, so you might do something like 8 as a low and 12 as a high. So we're going to scan from 8 to 12. We're going to do as a number of steps, just 3. There's an option for whether it's a linear or a log or a random number. We're going to do linear. There's an option for whether it's a float or an int or a string. In this case, we're going to use a float. And then you click on generate and it will show you the list. And if you get it wrong, 4 steps, that's not what I don't want these fractional numbers. So you can change that back and forth until you get it. What I want to do is 8, 10, and 12. 10 is my starting point, and I want to do 2 below and 2 above. Hit OK. It warns you that something has been changed, and just say yes. And now I'm looking at my JSON file, and it's added in this new chunk. I'm changing a parameter called JMC. The original value was 10. It's going to do 8, 10, and 12. Usually you want to scan more than one thing. So let's also do condensing. Same thing, highlight the value, add to scan. This one's going to be JCC, J value for condensing to condensing. My value started off at 5, so maybe we'll do 3, 7, with 3 steps, linear, float, floating point number, generate 3, 5, 7. So we started off at 5, we're going to go 2 above and 2 below. Click OK. Another warning about the JSON getting changed. That's OK. And now it's added in my new value into this JSON list. This list is editable. You have to be careful that you don't corrupt it. But if you ever decide, you know what, I really don't want that line, you can delete that line, or you could add more lines. The only thing that's tricky about this particular number list is it can't end in a comma. Your last value can't have a comma on it. Okay, so that's how you add values in your XML. What if you wanted to add something in your Python? What if you wanted to say something like, well, I don't actually know how much lambda volume is going to affect the sort. So let's do a parameter scan of that as well. Again, you want to highlight the numerical value, not the name of the value, but the numerical value. Right click, add scan. And this is lambda volume, oh, lambv, starting off at 4. We'll just do a little above it and a little below it. So we'll do 2 and 6, say, with 3 steps, linear, float, generate. So we started at 4. We're also going to look at 2, 4, and 6. Another warning that it changed to JSON, which is OK. Now it's in my JSON. So this is going to do 3 times 3 times 3. It's going to do 27 simulations. And as you can see, we're not actually doing real fine steps, and we're only doing 3 parameter values, but we're already up to 27 simulations, which would be a big problem if each simulation takes 2 days. This simulation doesn't, but it is something you have to keep in mind, that eventually your simulations will get too big. Now we've got everything in there. That was a good idea. Save your file, save all your files with the safe icon here, the multi-disk icon. Now we're ready to run. Now there's a problem. I'm going to run it, but there's actually a problem. And I'll explain what the problem is in a moment. To run it, you run it just like you run any other CompCell simulation from Twedit. Open player. I'm just going to think about it for a moment. Or I've lost a window. Yeah, there it is. It just took it a while. I had to think about it for a moment. Instead of immediately going to player like normal, since this has got a pscan specified, it opens this new window. This little dialog window. It should be properly filled out with the parameter scan simulation. So that's my full name to this, all the way down from C all the way down to my test name that I gave it. There should be an output directory, and by default, if you're working on your local machine, it'll be in your CompuCell workspace with your name of your simulation, test in my case, with parameter scan appended to it. So this is going to create a new directory in this output workspace. There are some options for whether or not you're going to output screenshots, which right now is a bit buggy because it actually depends on whether or not the original simulation had screenshots turned on or not. Just for the heck of it, in this case, I'm going to use the GUI, so it's actually see every simulation run. This, by default, the output, the CC3D installation dirt should be probably filled out already. One handy thing is this display command line button. So there's the command that you could issue in a command window. A DOS window on a Windows machine or any command window in a Linux or Unix machine. And that will run the simulation. You'll want to think about the platform a little bit. You might want to do things like no-hup or some of the other capabilities that let you simulate or launch a run without having to sit there and watch it. But that is the command that you would use. In this case, we're not going to use that command. We're going to go ahead and run it live, so to speak. Again, this will take a moment to start up. And my CompuCell window, and there it goes, it's running. And it says, see at the top of the window here, it says iteration 0. And I'm going to let at least one simulation run. I think I have this set for 5,000 Monte Carlo steps. See, my hetero contact's doing pretty good. This sort is doing pretty good. You see, it's still got some stuff out here on the periphery. It's sort of embedding the blue condensing cells. Certainly my hetero contact area has gone way down, and it's about to hit an end here. You know, I guess I have set at 10,000 steps. That's unfortunate. Yep, I had set for 10,000 steps. I'm going to stop it in a moment anyway. You see the top of the window that says this is iteration 0. I'm going to let it run for a moment. Here is my standard CC3D workspace folder. And see, it's created a file called the name I said, my root name test plus added parameter scan to it. So that simulation just ended, and in a moment it'll start up another one. There it goes. And now it says it's on iteration number 1. We start off at iteration 0, now it's on iteration number 1. So I'm going to kill this, which is actually kind of tricky to do. I don't know if that's actually going to stop it by closing that window. We'll have to wait and see if it comes back. And I'll go and look at my output directory. Yeah, see, it continued on. So about the only way to get it to kill is to kill the TWEDIT and the simulation both. I'll go back to that in a moment. This is my output directory. So there's the results for scan iteration 0, scan iteration 1. And if I had screenshots, there would be screenshots in there. And as you can see, it started up another simulation. It's not going to let me, it doesn't want me to be able to stop it, which is actually kind of what it's supposed to do. So what I'm going to have to do is to kill all my Pythons. So it's hard to kill one of those runs. If you accidentally kill a run, you can go back to TWEDIT and just relaunch it, and it'll pick up where it was. Restart TWEDIT. So we're back to where we were. Now, if I do open in player, it'll go through the dialogue again, and it will pick up wherever it was when I killed it. So we'll keep on running. Another handy thing that you can do is if you're doing it in the command line and you figured out no hup and how to do, actually you don't even need no hup, you could open two command windows and paste this command into both of them and have two simulations running, well, two streams running at the same time. And pscan will keep track of what's going on, and each one of those two jobs will just alternate about which one they're doing. On a single machine, that doesn't make any sense to do that because it's just going to take twice as long for each simulation. You're doing two simulations at once, but it'll take twice as long to do one simulation. If you're on a cluster, you can issue this command as many times as you want. And if you've got multiple CPUs and multiple threads, the system will just fork that all out over whatever you have. We have a small 32 node cluster, and we can issue this command 32 times and have 32 simulations running simultaneously. And pscan will make sure that they don't collide and they don't do any duplicates, and that everything actually gets done. So that's all hunky dory. I'm going to cancel. I'm not going to run it here. Whoops. Uh-oh. Hopefully it didn't start up. Now, I said there was a problem with this. I'm going to get my PowerPoint back. So there's slides in the deck about it, what I just went through, if you ever want to look at it. There's the final values. And NanoHub, if you set the scan up on NanoHub, I think it works. But if you set the scan up somewhere else, you can't transfer it to NanoHub. Same kind of thing in your output directory, you'll have all your files. Again, as I said, where all the output files are. If you want to redo a parameter scan looks at that output file and sees if it exists. And if it does, that's how it decides if it's done or not. If you want to do a new scan, you have to either delete that old directory or rename it. So for example, just add save to it or something, so the pscan will run again from the beginning. Okay, so this is where we want to be now. So what we did just worked great. It ran a parameter scan. The only problem is we don't actually have any output because we didn't tell it to write anything. What we'd like to be able to do is write to a single file, appending it every time with the values of our parameters and our nice metric. So we'll have to go back and add writing to a log file. So there's another project file that's already set up to do that, and it's in that zip file. It's cell sorting base pscan write output. And that just goes by the things we started off with today about how you write to a file. You can use the twedit helper for Python utilities, open an output file and open it for append. So it just keeps getting, every time you run, it gets updated. And let me open that one. Get rid of this one. And that will be this one, cell sorting base pscan write output. It's the same basic simulation. It's the cell sort. It's got the graph in it. But now what we're going to do is write the output to a file. This also has the parameter scans already defined, so it's still in there. And remember, this is how it marks the things that are being changed. It's the double curly brackets and then the name we gave it. So that in this particular file, I was changing 3 things. To capture that, well, when the pscan Python script runs, it just replaces all occurrences of curly brace, JMC, curly brace with whatever the current value of that is. So you can refer to this structure anywhere you want in your code, including in your little chunk of code where we're going to write to the output file. So we've opened a file. It's for append. We're going to write a line that's tab delimited of our headers, but they're going to be the MC, CC, and CN J values plus our header surface contact. And then another line that converts those values to strings. Again, the pscan Python will replace this with the proper number when this particular job is running. And we're going to write that all to the outline. We're going to print it to the terminal, but then we're going to write it to our file.
Hey, Jim, there are a couple of questions in the chat.
Okay.
I
Okay,
think,
I'll back up a little bit.
yeah, I mean, I think maybe you went through it very well, but maybe it's worth actually just walking back and going through the steps again. You don't have to do all of them, but just walk people through the workflow when you have a chance.
Okay.
And there were some questions about, some of them are technical and maybe not appropriate to answer here. But you might want to look at the chat and just ask a couple.
Okay, so at this point in the development process, we have a scan developed or defined. And we have a way of writing the results to a single file. So at the end of the day, we know how well each simulation did. But if we want to go back to the very, very beginning, remember we start off with the simulation that we have that's working. And we're going to make a copy of it because we're going to make quite a few changes in there. We want to keep our original file. Over here in the CC3D project menu, if we right click, you get this drop down and there's add a parameter scan. And when you click on that, that will add this new JSON file. And you can open it up and it'll start off closed. You open it up and then double click the file to actually see it. And it'll start off empty, basically empty. Now we want to go through and add all of the parameters that we actually want to scan. And we do that by, for instance, if I want to change the medium to condensing J value, make sure you select the numerical value, not the name of the variable. Numerical value, including all of its, make sure you get the trailing 0 and stuff like that. Right click and add a scan. Now, as you can see, there's another thing here, and I'll just try it real quick. There's also, select that, right click, remove from scan. And it'll ask you if you want it for sure. What it'll do is it'll get rid of the tag and put the value back in. I'm going to say no. But it'll put the value back in that it had saved. So it had saved the original value when we defined the pscan. So we can undo it. And if I do that undo, for instance, if I undo the JCC, it'll just take this chunk out of the JSON file. And in this place here, it'll just put that value of 5 back in. I'm not exactly sure what it would do to a situation like down here in our output where we refer to it again. I think it might just replace this down here with that initial value of 5 as well. But normally you're putting things in, so highlight, right click, add to scan, give it a name. That's the string that'll put back into the file inside curly braces. Tell it your starting value and ending value. So perhaps 4. I'm going to go 4 to 6. And how many steps you want to do. You can do a lot of steps if you want. And whether or not it's linear or log, whether it's an int or a float. In some cases, it would matter if it was an int or a float. In general, in Python, it would not. However, if you had something like an iteration counter, you wanted to do 10 iterations, you want to make sure that those are integers. And then hit OK, and it'll go ahead and do the changes to the file. So once you got it all set up, make sure you save your file and start it the way you normally do. Open in player. And this is one of the places that changes from the normal behavior and tweet it. Instead of actually going right to player, it gives you this dialog. Now, if I was going to run from a command line, I can just display the command line, copy it, and then cancel. And this guy should not have come up. Hopefully it's not actually going to start to run. Doesn't look like it's gonna. That's good. But now I have in my copy paste buffer command, the whole command. If you want to run on a cluster, let us know. We don't have any really great write-ups, but we've done it a lot, and we can give you the no-hup commands and all that kind of stuff. It's reasonably straightforward, but you want to make sure everything is working really well before you go to a cluster and launch 10,000 jobs, each of which are going to take 3 hours. You definitely want to make sure everything is set up to work right. Okay, so in this particular version, yes, this has the parameter scan in it. It has a little chunk of code that calculates the quality of the cell sort just by summing up the heterologous contact area for condensing cells to all of the condensing cells. And it has a little chunk of code in the finish to open a file, write the value to it, and then close the file. At the beginning of this session, I talked about using the start to open a file and then write it in step and then close it in finish. But in this case, all we want to write is how well the simulation worked in our parameters. So in the finish, we do everything. We open the file, write to it, and close it. So down here is an open, put the our output string into it, and then close the file, and we're done. Now I'm going to try to run this one, but since we don't want to watch it for too long, I'm going to make it go even faster. Let's say we'll just do 2,000 steps per simulation. And I just did open in player, and it's going to intercept me and not go to the normal place, which is okay, just fine. We'll go ahead and use the GUI again. Go run. Yes, James made a good point in the chat. I will go and find my output directory. And I'm getting too many windows open here. Yep. Here is my my command box, my typical log that you get from CompuCell, and it says, wait a minute, the parameter scan is completed down here at the bottom. The reason it says it's completed is because I'm trying to write to the same output file that I used before. And that file has all the scans in it. And as far as it's concerned, it was done. And James's comment was in each one of these files, so scan duration, oh, there's my JSON file, there's my CC3 dial. I can keep drilling down. There's all of my steppables and everything else that goes with that job. So this scan iteration directory has everything that was done for that particular simulation. So in any case, so the problem is it won't run another parameter scan because it's pointing at the same output directory. Here I have a couple of choices. I could just rename this. Yeah, I want to keep this one that's got a different name so CompuCell won't see it, or I could just delete it. Whatever seems to make sense at the particular time. So let's go back. I've hidden that file. Open in player. Think about it for a moment. There it is. Really nothing I need to do. I'm going to hit run. And I got the same message again. It still thinks that that parameter scan is alive someplace. So I need to go figure out where that guy is hiding. This is one of the things that gets really difficult on NanoHub is because the file structure is so arcane and you don't have access to all of the different file structures. I'm just going to delete a whole bunch of my old ones. Back to Twedit, back to open in player. And I got the same message. So I'm going to do something a little different. Open in player, the output directory. And nuke them all. This is interesting that I'm getting this clash. It should not be getting this clash. This file shouldn't be there anymore. See if that's enough. Back to open in player. This is cell sorting based pscan write output. Cancel. I had slide one open. There's back. So there's the output directory. That's the thing that has to be non-existent or only partly done. And actually right now we want it to be non-existent. We want to create it. And there we go. Looks like it's going to start. And I forgot to turn on the GUI, so it's running without the GUI, but that's okay. It'll actually be a bit faster without the GUI. And this is our standard CompuCell CC3D workspace output, cell sorting, parameter base, pscan. And you can see it's updating. So 0 scan, 1 scan, 2 scan. And we were writing this scan file, this log file. I double clicked on it and get it to open up here. You see there's another one file. So there's my log file. I remember we wrote a little header that was the 3 things we were changing, and then the header surface. This is tab delimited. I don't want it in Excel, automatically opened in Excel. And then here's the values for one run, and it's appending to this file. So if I reload the file, it's continuing to add lines to it. Now you might say, well, it'd be nice not to have all these duplicates of the header line, but eventually what I'm going to do is take this whole thing into Excel, and I can just sort it and delete all these extra headers. But so you can see, so it did JMC was 8 and JCC was 3 and JCCN was 5, and I got 668 as my heterologous contact area. The next run it was 650 and then another 650 and then a 902, and it's just going to keep chewing through all of these possibles. And this guy's doing 27 simulations, so it actually isn't going to take it that long. It's going to take it another 5 minutes or something. But we probably don't want to wait for it. Okay, So this guy's running. I'm just going to let him run in the background. Here's my command log. So it just it'll count up to 5. Yeah, we're only doing 2,000 steps. So that finished, and now it's doing another one. So I'm just going to keep chewing through it. So let's go back to our slide deck. So we had changed our parameter scans with writing files, writing a log. That's all in the slides if you want to go back and look at it in more detail if you forget how to do it. And this is what this job is going to eventually create. Is that file I just showed you. This is our log file, and there's 27 lines total. Take that and paste it into Excel. Sort it. And in this case, I've sorted by this heterologous surface area. This is the number we're trying to minimize. So the best one I found was 278. Here's a graph of the blue line is just in order of runs, that heterologous surface area, our metric. See, it's oscillating up and down from the periodicity of the parameter scan. If you take all these things and sort it like they are here and plot that our quality metric, see there's looks like 6 or 7 simulations that basically give the same result in terms of our quality metric, and then a bunch of simulations that give much worse results. So we have it sorted here. Here's the best run, 278, and our 3 values that were 278. Just looking at it, you can make some conclusions of this on this sort, that JCC was always 3 or 5. JCN was either 7 or 9. But JMC had all 3 of its values, 8, 10, and 12. So it looks like these two, JCC and JCN, are doing more than JMC. And you can, of course, start playing with all the numbers and do, well, what's the correlation between each of these J values and the quality of the fit? Well, here's the correlations. JMC to the hetero surface area correlation is 0.1. JCC is 0.4, 0.5, basically. JCN is 0.75. So JCC and JCN are the one are really driving how good this sort is. And you could just say, well, these are the best values here, 12, 3, and 7, which are pretty close to what we did before. You could also do a nonlinear regression with parabolas and try to interpolate what the optimal values are. But that's downstream. So that's the basics of a parameter scan. It's relatively straightforward. It's a little tedious sometimes because of deleting files and making sure you've got file data being written somewhere you can use it. If your simulations take a couple hours, your parameter scan could take a very, very long time. And so you'll want to be so much selective about what things you're scanning. It's also entirely reasonable to do a very coarse scan over a few parameters, and when you get a better idea what those parameters should be, doing a finer scan separately, taking smaller steps. Okay. So as everyone knows from the past week, CompuCell is stochastic, and depending on exactly the characteristics of your model, you can get anything from very small run-to-run variations just from the stochasticity to very big changes from the stochasticity, from run-to-run. So it's often very useful to be able to do replicate runs, do the same simulation 5 times, 10 times, however many times you think are necessary. And it turns out that the parameter scan is actually a really handy way of doing that, since it will take care of spawning the jobs, how many it's done, how many it's supposed to do. If it gets interrupted, you can restart it and it'll pick up where it left off. And if you've already built into your code a metric function and the ability to write that metric out to a file, you can collect all your simulation, your metric from across a large number of simulations, even if you're not actually scanning a variable. So it's easy enough to do. One way to do it is we'll just add a dummy variable in our Python, like replicate count. And originally it had some value, and I highlighted it and right-clicked on it and said add to parameter scan. And in our output, we're going to print that replicate count as well, just so we have it in our output. And our JSON file just now looks like we just have a new variable with some values. So this particular job looks like it's doing 2 values of JMC, a single value for JCC. There's nothing wrong with doing a single value in a parameter scan. It's just do it once. Same thing with JCN, and then it was going to replicate it 3 times. So this then launches exactly the same way. Right-click in Twedit and click Run, and you'll get the dialog, and you can copy the command line or launch it and go ahead and run it locally and immediately. So that's how you do replicates. You don't have to have any other scans, right? You could do a parameter scan that did nothing but the exact same simulation 10 times. So we have that. There's a version of it in the zip file called, I keep getting my name longer and longer and longer, cell sorting base, pscan, write output replicates. I think I'll go and open that one. So this is exactly the same as the ones we've been looking at, except for now in our parameter scan file, we're going to do 3 replicates. And now I'm not going to run this because this is 27 times 3, 75-ish simulations, and it'll take a while. But it's still going to write this an output file very similar to the one we had before. Let's find it. This one. The output file looks exactly like this one, except there's one more column, and that column is iteration count. So you'll find 3 rows where I had these 3 values, and each one will have its own score, because the cell sorting is actually quite sensitive to, it varies a lot from run to run. So you'll have 3 runs, same J values, 3 different outputs. You could take the average of those outputs as a measure of how good the parameter set is. Or you could say how good the parameter set is the best value. It's kind of tricky to figure out what the best way of deciding what the best value would be, whether you use the average or the minimum for a set. So that's, again, fairly straightforward if you're doing I lost my spot here, replicate runs. So if you want to do 50 runs, you can do it. And the pscan is a nice handy way of doing it. And you can, of course, do as here, replicate runs as you're doing the parameter scan. Okay, so getting kind of late, 5:30, we still have some time. I'll go a little bit farther. Parameter sensitivity. Parameter sensitivity is how much the output of a model changes if you change an input parameter by some fixed amount. This is a good approach to deciding what parameters in your model actually make the most difference. Sometimes you'll have parameters in your model, and the model is really quite insensitive to exactly what that value is. You really love those parameters, though, because that means you don't need to know what they are, or at least you don't need to know what they are accurately. In the parameter scan we did earlier, I think it was the medium to non-condensing, the metric was pretty insensitive to that value, which is great. That means I don't need to know that value to great precision. It just has very little effect on the model. I still need the value in the model, but I don't need to know it with high accuracy. Parameter sensitivity, on the other hand, will tell you that this parameter just does not affect the model very much. Parameter sensitivity will also tell you which parameters actually make a difference. Parameter sensitivity is reasonably straightforward. You can get lost in the details because there's a number of ways of defining what you're trying to do. What we're going to do here is just talk a little bit about it. You could use pscan to do it. basically just give every parameter two values, the reference value and a change value. It's not the most efficient way to do it. For a small number of parameters, say 10 or less, it's probably easiest just to do it manually. Change the parameter, make a run, write down the metric, then go on to the next one. So a little bit more about parameter sensitivity. What you do is you have a reference set of values. So here we have three values in three parameters in our model, and we're going to do a run at the reference value for those three parameters. And then for each parameter, we're going to do one run where we change that parameter by some amount. And if you look in the literature, frequently people do 0.1%. They change their parameter by 0.1%. You might have noticed in CompuCell that a CompuCell is not going to respond to small changes like that. It's going to get lost in the stochastic noise. So you need to do pretty big changes, much bigger than a hard ODE model might use. So maybe we'll do 20% changes. So we'll take our value and we'll do run with P1 value changed by 20%. And then we change P1 back to where it was and do the same thing for our parameter number 2. Then we change it back to where it was, the same thing for parameter number 3. The nice thing about sensitivity is if you have 10 parameters, it just takes 10 plus 1 simulations. So you do sensitivity a lot faster than you do a parameter scan. So that's the overall plan. No reason you can't do 20 or 30 parameters, even if you're doing it by hand. So what is the sensitivity actually defined as? The sensitivity is defined as the change in output divided by the change in that parameter. So each parameter has its own sensitivity. This number is the standard way of doing it. The problem with doing it this way is that your parameters have a wide range of values. You'll have some parameters that are 10,000 and some parameters that are 10 to minus 6. And so if you just go by the change in the delta parameter, you've got a difference of orders of magnitude in how big this number is. So the usual way of doing this is to normalize. It's the change in the parameter divided by the reference parameter, and it's the change in the output divided by the reference output. Basically just making fractions of both of these values. If you do that, you can now compare the sensitivities for different parameters, even if those parameters have radically different numerical values. You'll be able to say that if I change this parameter 10%, the model changes by 20%. If I change that parameter over there by 10%, the model changes by 5%. Therefore, my first parameter is more sensitive than my second parameter, without getting lost in the fact that the parameters themselves have different magnitudes. So in practice, it's just if all of your delta parameters are the same, your fractional parameters are all the same. The sensitivity is just how much the output changes divided by the normalized or the normal output or the reference output. It probably sounds more complicated than it really is. It's pretty straightforward. So the thing though is that you're doing a sensitivity at a fixed point. So back here, our fixed point is these three values, whatever they happen to be. And we're looking at sensitivity as you change around this fixed point. If our fixed point is different, our sensitivities may well be different. In general, our sensitivities will be different. So when you're doing a sensitivity, you want to make sure you're at a fixed point that makes sense. Typically, that fixed point is at a set of parameters that either generates a reasonable output as far as you're concerned, or perhaps a set of parameters that reproduces an experimental result. And of course, that would be where you'd be most interested. You want what's the sensitivity of my model to the parameters at a set of parameters that gives me a biologically relevant result. So the first thing, if you're going to do sensitivity, is you need a reasonable fixed point. The second thing to consider is exactly what is the output you're using. In the cell sorting, we've been using the heterologous contact area. But in other simulations, you might have multiple metrics that all make sense. In the cell sorting, you might say how many cells are left at the end of the simulation. If you crank up adhesion too much, you might start squishing cells out of existence. And that would be a bad thing. So you might want to do a sensitivity of what's the best set of parameters that sorts the cells without squishing any out of existence. But that's 2 metrics. And so each one of those metrics would have its own sensitivity. So things can be complicated, and the more complicated your model is, the more outputs you might be interested in, which means more sensitivities you would have. I think I'll skip that. That's just the numerics. So we can do sensitivity with the parameter scan. It's not the most elegant way of doing it, but it is one way of doing it. Basically by saying, here's our reference value for this 1J value is 10, and I'm going to change it by 5%. So my second value is just the first value plus 5%. This one was 3, and if I add 5%, it's 3.15. 9, if I add 5%, 9.45, so on. And I want replicates. So this P-scan will do a sensitivity analysis, and it will do 3 replicates, so you have some way of dealing with the stochasticity of the compressor stimulation. Reasonably straightforward. The problem is with this approach is it's going to do exhaustive sensitivity, which is every single parameter gets tested once. But it also tests every situation where 2 parameters are changed and every situation where 3 parameters are changed. Usually you want single parameters. Sometimes you want pairwise parameters because that tells you if parameters interact with each other. You almost never want these higher order ones. They're too complicated and too hard to interpret. So in using the P-scan, it's kind of overkill, and we're getting a bunch of values we don't actually need. But again, it's an easy way of doing it, and it's an easy way of building in replicates. It just means you'll have to do some post-processing when you're done to kind of sort out all of your various values. You'll need to find the one simulation that has all your reference values, and then the individual simulations where exactly one other parameter is changed. It's doable. It's just a little fiddling in Excel. Again, it's getting pretty late. So we can do sensitivity analysis. Very handy to be able to come back into your model and say what sensitivity is. This is the result of doing the sensitivity analysis on this cell sorting model. So here we have the reference simulation with our 3J values and a single run. I'm pretty sure I did this as a single run. The metric, quality metric was 301. And then what happens if you change this guy by 5%, change this guy by 5%, change this guy by 5%, use the formula that we had earlier, you find the sensitivity for JMC is very low, 0.2. Sensitivity for JCC is much higher, 4. What the 4 means is if I make a 5% change in that J value, I get a 20% change in the quality metric. So these 2 parameters are quite sensitive, and this parameter is quite insensitive, and these 2 are quite sensitive. The other thing you can do, if you actually work through all the numbers and do the pairwise sensitivities, you can determine if parameters interact with each other. If the parameters don't interact, their effects sum. You can just add up the effects for the individual changes and predict what happens when you do the double change. And the exhaustive scan will give you both of all 3 of those numbers. If the parameters do interact, then you can't just add the individual effects. And there are a lot of places where parameters interact. A common one that you might have is if you're using Michaelis-Menten equation anywhere, the Km and the Vmax are highly correlated with each other, and they strongly interact with each other. And depending on your system, you may or may not be able to determine values for Vmax and Km. It's not surprising that they interact because they occur in the same equation. So the more interesting ones are when you get interactions between parameters that are not in the same equation. So situations like in our cell sorting, where an adhesion is interacting strongly with, say, your lambda volume for the cell type. It's warning you that there's something more complicated going on there. Not necessarily wrong, but it's just that there's something more complicated going on. And it's getting even later. Some quick caveats on this thing that That was for demonstration purposes only, because you're only doing 5,000 steps, and it really should have been done for a lot more steps. I will skip to conclusions, and that's just a list of all our files. I wanted to real quickly go over, as you've been working this week, you probably noticed it's easy to get lots of sequential changes in a file and starting to lose track of what files are what, and not having a file that you can back up to if your simulation gets broken in some way and you can't figure out the problem. So for best practices, you really should develop some routine for versioning your projects. If you're a programmer, programmers love GitHub and SourceForge. It's a great system. It's got a really steep learning curve. Alternatively, you can just put the files onto something like Google Drive or Dropbox, which automatically versions all your files, since Windows and Mac don't usually, and Linux don't usually version your files. You put it on Google Drive, you can scroll back 72 variable or 72 versions of your file if you want to. That's okay. Problem is you get all these old versions, you don't actually know which one to scroll back to. Kind of a simple and easy one to do is just periodically just version. Actually, I'm going to skip one more. Is just version your project every so often using the zip it in Twedit. You get the point, you've got all the bugs out, it's printing the right thing, it's not throwing errors because you're missing a quote mark or something like that, and it's doing something useful, you've added a new function in Twedit, just make a zip of it and write the date on it, rename it with the date. So you just have this sequence of old zip files. You know, this is where I got cell sorting to work, this is where I got writing the metric to the file working, this is where I got the pscan working, and just version it that way, so you have old versions. Very straightforward, very easy, non-programmer, not sharing it with anybody routinely. It's a great way to do it. Much better than just ending up with only the most recent file of your most recent version of your simulation. It's also a good idea in your simulation folder to just keep a Word document or something of the basic description of what you're doing. What are your cell types? This is a wound healing model, and I got 6 cell types, and I've got 2 diffusing species. Just a word description, a prose description of what you're trying to do. You can expand and contract that description as you go on. You find out you have to add something to your model, take something out. You just keep that nice little biological description. You can also use it as your elevator pitch when you're showing it to someone else. You can quickly describe what you're trying to do. Next thing is parameters. As you notice, you have parameters in your file. They tend to be spread out. They're in different places. Some of them are in your Python file, some of them are in your XML file, some of them are in some other file someplace else. It's difficult to keep track of them. It's difficult to make sure you're not making mistakes like mixing units or not handling units correctly. So though we're getting really late, and so you can look at these slides at your convenience. One thing you can do is just at the top of your Python file, just define some parameters. Like here I have converting seconds to MCS. That's my conversion factor. If I want to convert days to MCS, that's my conversion factor. And my cell diameter is going to be 5. I can then refer to these things anywhere in this Python file as just S to MCS. I can't change it in other places, but all of my steppables and things like that will inherit this variable. So this is one approach. It's a beginning. It's better than doing nothing, but it's not the greatest. A little better way is to create a parameter file and put your parameters there. And you can do that as just as a Python file that you can add into your simulation. There's a demo here. I think people have noticed this little checkbox that you haven't used yet that says Python only. So this will create a simulation where that XML file doesn't exist. And instead, what you get is all that XML stuff as Python. The nice thing about it being Python is you can do things like put a variable in how many Monte Carlo steps you want to do, for example, or the X dimension of the model. That can be a variable now, and you can change that variable in code. Whereas in the XML version, you can't do that. So that's a handy way if you combine that with a parameter file of doing just that. Having a parameter file that says my model width is 50 by 50 instead of having it hard coded into the XML. There's a demo, the CC parameters example, it's in that zip file that does a pretty exhaustive set of parameters. I just lost my spot. To use a parameter file, you basically, well, actually, let's actually do it. It's probably more use if I actually go through doing it. So over here in my left thing, I can say we had add parameter style before. We don't want to do that now. What we want to do is add a resource. So you click add a resource and it says, what do you want to call it? We'll call it parameters, except I can't type. Its file type is just going to be Python. It's going to live in the simulation directory where all of our other files live. Finish. Now I have a file here called parameters. Double click it and open it up. And this is now my parameter file. Now I can do something like, say, and the volume equals 4. And I can also do calculations here. Lambda volume is something scaled by the width of the model or something else. To use it in my regular steppable file, I just need to import parameters as P. I can't type. And now I can use that value as, trying to find where I used it. So in my parameters file, I have a thing called lambda volume. In my steppables, I'm going to import my parameters as P, and I can refer to lambda volume as p.lambda volume. And I can make a change here. Unfortunately, I can't do that, this particular version. This is our old XML version. I can't do that with these values. But that's why you'd want to do a Python only simulation so that this file was in Python and therefore you could import the J value. You could also import things like the model width and all, and you know, the dimensions, these dimensions up here, the number of steps you're going to do, the temperature, anything you want. And you can calculate all those. So this is just showing, so I import parameters as P and then how I'd use P. P, our parameter file can include conversions and equations. So if I define my model in terms of cell widths instead of pixels, and I say my cells are a certain width and my conversion for pixels to microns, I can calculate how wide my comp cell model needs to be. And I can use that at the startup of the model. Now I can come in and change my resolution of my model by changing these values. Let's say it's 5 pixels per micron. I make it run really fast because the cells are only a couple of pixels across. The other thing you can do in this file is write down what you think the units are, or what the units are supposed to be. So this is supposed to be in microns. And it's the cell width in microns. And oh, if you have a reference, you could put a reference in. So if you had a diffusion constant that you pulled out of a paper, you could put the diffusion constant in and say that's in microns squared per second. And oh, that came out of PMID such and such a paper. It's a good way to keep track of all your parameters and things in your model. So there's an example in my set of zip files. TJ has an extensive parameter file in his viral model file as well. This is one way of doing it. There are more complicated ways of doing it using a dictionary so that you could actually keep track of the name of the variable, the value, the unit, and the source, all as a dictionary of things. We won't go into that here. It's more detail than we need. But in any case, so this is something to consider, making a parameter file and keeping all your parameters separate, not having them scattered all throughout your codes. Okay, I'll check the chat real quick. So should the parameter file have a specific structure? I kind of messed it up here, but I think it should. You should have a section for biological parameters. That's where you decide things like my cells are 10 microns across, or my model is 20 cells across. Those are purely biological descriptors, and it has biological units like microns or seconds. I would then have a domain that's your conversion factors. You decided it's 1 micron per pixel. So you can generate a conversion factor with that, or it's 3 microns per pixels. Also, what is your conversion from seconds or hours to Monte Carlo steps? What's your time conversion? You can hard code, or you should specify what that is in this file. Those values can change, but you should actually have them defined explicitly in the file. So if somebody says, what is 50 MCS in seconds, you can tell them, well, it's supposed to be 50 seconds, 50 minutes, 50 hours, whatever it happens to be. And then, so biological parameters, conversion factors, and then model parameters. And this is where I kind of messed it up. The model width in pixels is a model parameter, and that can be calculated by, the model is supposed to be 20 cells wide. Each cell is 10 microns wide, and it's 2 microns per pixel, or whatever the value is. So you might have those 3 kind of characterizations: your biological parameters, your conversion factors into comp cell units, and then what that results in terms of the parameter in the model. So that's one way to do it. There's no real, strict definition of how to do this. It might be worthwhile sometime in the future for comp cell to have a class for a parameter where you could keep the unit, the numerical value, the name, the unit, and some reference to it, and just generalize that into CompuCell. Okay, since it's getting so late, I think I will stop there. So we covered a lot of stuff. Some ways of writing to files, and you can go into my deck here and get the code. It's also in the demos. Parameter scans, reasonably straightforward, can be a little picky about certain characteristics. You can also use parameter scans to run replicates. We talked about sensitivity analysis. We saw a real simple example in cell sorting. Definitely something you want to consider when your model is getting more mature and you've got components in it and you think it's giving reasonable results. Sensitivity analysis is an interesting thing to look at. Tell you what you need to know precisely and what you don't. Parameter files, a better way of keeping track of things, and best practices about doing something like versioning and whatever you're comfortable in versioning, whether that's zip file or GitHub, whatever it is that you like. I know TJ et al. Use GitHub for the viral model. It's extensively versioned and tracked.